Hi everyone. In today's session, we'll see the AC drives. In that, induction motor drives. So the circuit diagram shows that the equivalent circuit diagram of an induction motor. So your supply voltage is V1 and the corresponding frequencies of the stator and rotor both are F, and here stator resistance and reactance are R1 and X1. The corresponding stator current is I1. The no load current is I0. The corresponding magnetizing components are R0 and X0 or IW and I mu currents, and corresponding primary winding current is I1. So all these are stator quantities, and the induced EMF in the primary is E1 and the secondary is E2. The corresponding rotor current is I2 and reactance is X2, whereas resistance is equal to R2 by S. So the same R2 by S resistance can be rewritten as R2 plus R2 into 1 minus S by S. That is nothing but here R2 plus R2 into 1 minus S by S means R2 by S minus R2 into S by S means minus R2. So minus R2 plus R2 will be get cancelled. Only R2 by S is the remaining term. This R2 by S can be rewritten like this: R2 into 1 minus S by S. Okay. Here this is the equivalent circuit diagram. Here we are not the rotor frequency also F. If you are multiplying with the rotor quantities with S, then you will get the SE2. That is on the secondary side, all the quantities are multiplying with the slip. Then SE2, SX2 and S into R2 by S will give the R2. The corresponding current I2 will become I2 is equal to SE2 by R2 plus SX2 square under root of R2 square plus SX2 square, because we have multiplied with all these quantities with the slip. During that time your frequency also it is slip times of the stator frequency, SF it will become. So here the air gap power is calculated like this. The air gap power Pg, let us take Pg is equal to the corresponding current into only real power. Real power means 3 into I2 square into R2 by S is nothing but the air gap power or rotor input power. Air gap power or rotor input power. Air gap power or rotor input power. Then the corresponding rotor copper loss. If you want to find out the corresponding rotor copper loss means we need to consider only pure resistance. So if you want to consider the resistance, the corresponding R2 by S is divided into R2 plus R2 into 1 minus S by S. So this R2 into 1 minus S by S is nothing but fictitious resistance. So here R2 into corresponding current square, that will give the rotor copper loss. Rotor copper loss is nothing but, so here 3, why I used 3 means this is 3 phase induction motor means 3 into I2 square into R2 by S. Likewise in a similar way to find out the rotor copper losses, 3 into I2 square into R2 will give the rotor copper loss. So the air gap power minus rotor copper loss will give the output of the rotor, that is nothing but net mechanical power output, because output of the rotor is nothing but mechanical power. So that's why the air gap power minus the intermediate losses are nothing but rotor copper loss. Rotor copper loss if you neglect, then we'll get the net mechanical power output, that is nothing but 3 into I2 square into R2 by S minus rotor copper loss is nothing but 3 into I2 square into R2. That will give the mechanical power output PM as 1 minus slip times of the rotor input or 3 into I2 square into R2 into 1 minus S by S will get it by subtracting this one, and the difference between this air gap power and rotor copper loss will give the 1 minus or PM is equal to, if you are subtracting this 3 into I2 square into R2 from this term, you will get 3 into I2 square into R2 into 1 minus S by S. But if you see here 3 into I2 square into R2 by S is nothing but air gap power or rotor input power. So that's why 1 minus slip times of the rotor input power is nothing but mechanical power, output power. So 1 minus slip means slip is rewritten as synchronous speed minus rotor speed by synchronous speed. So from that we will get, if we from here ns minus ns and minus of minus means it will plus n by ns into 3 into I2 square into R2 by s. So this is the mechanical power output. This mechanical power output we will use it in the torque equation. So here we will calculate this, or we derive this approximate torque equation. This approximate torque equation is well enough to in almost all the calculations it will give almost accurate calculations like the full load torque equation. That's why in most of the induction motor calculations we'll use this approximate torque equation only. So to calculate this approximate torque equation, power P is equal speed into torque, where speed is equal to 2 pi n by 60 into T. So if you want to find out the torque T is equal, this will go on the other side. That means 60 by 2 pi n into mechanical power output. P is nothing but mechanical power output. Already we calculated, we derived that mechanical power output. Pm is equal n by ns into 3 into I2 square into R2 by s. So that we replace here. So 60 by 2 pi n into n by ns into 3 into I2 square into R2 by s. So by simplifying this one, we will get torque T is equal to simply 60 into 3, that is 180 by n and n will be get cancelled, 2 pi ns into I2 square into R2 by s. So further, by replacing this I2, already we derived this I2 in this torque equation, we will get 180 by 2 pi ns into SC2 by under root of R2 square plus SX2 square whole square into R2 by s. So by simplifying this one, we will get the full load torque as 180 by 2 pi ns into SE2 square into R2 by R2 square plus SX2 square. This is your full load torque. So if you want to find out the starting torque, in the starting your speed is equal to 0. What about slip? Slip is nothing but ns minus n by ns, right? When speed is equal to 0, rotor speed is equal to 0, ns by ns. That means your slip is equal to 1. So by substituting this slip is equal to 1 in the full load torque equation, we will get the starting torque. The starting torque is equal 180 by 2 pi ns into, simply we are keeping this slip is equal to 1. That will give E2 square into R2 by R2 square plus X2 square. To find out the maximum torque we can get from the full load torque by differentiating this full load torque with respect to the slip, because on the right side only slip is variable. So dt by ds equal to 0 will give the maximum torque condition. That condition is in terms of slip, Sm is equal to the maximum torque with respect to the slip is nothing but Sm is equal to R2 by X2. By substituting this R2 by X2 in the full load torque equation, by replacing this S with R2 by X2 in the full load torque equation, we will get maximum torque as 180 by 2 pi ns into E2 square by 2x2. So these three equations are very very important, because by using these three equations only we will draw the torque equation, speed torque equation, and your speed torque equations will vary by using these three equations, because your starting torque is directly proportional to the rotor resistance. If your rotor resistance is varying, means your starting torque will increase or decrease. Your full load torque is directly proportional to the slip, and your maximum torque is independent on the resistance, but it is inversely proportional to the frequency. So likewise, so by changing one of the parameter on the right side equations, we can change the torque positions, whether starting torque or full load torque or maximum torque positions we can change. So this is all about the approximate torque equation. So by using this approximate torque equation, so if we draw the speed torque characteristics of the induction motor, so this is all about the speed torque characteristics of the induction motor. On the y-axis speed, on the x-axis torque, if you consider. So in the starting, during the starting torque is nothing but during the starting. So we are replacing the slip is equal 1 means we'll get some constants, right? 180 by 2 pi ns into starting torque, 180 by 2 pi ns into E2 square by E2 square into R2 by R2 square plus X2 square. That means you will experience some torque, starting torque. So during the starting means at speed is equal 0, we are having some torque, and when slip is equal to R2 by X2, during that time we will get the maximum torque. When slip is equal 0, When slip is equal to 0, your torque is equal to 0, right? Because torque is directly proportional to the slip. Slip is equal to 0, your torque is equal to 0. Simply this y-axis is 0 to omega ms speed. 0 speed means slip is equal to 1. And synchronous speed means omega ms minus omega ms by omega m, right? Omega ms. That will give the slip is equal to 0. So we can get the induction motor characteristics like this. In this, the stable operating region for the motoring is nothing but from maximum torque to this position, or from slip is equal to 0 to or near to the synchronous speed, will get the stable operating characteristics, that is forward motoring characteristics. This is unstable operating region, because if you see here, as speed is increasing, your torque is also increasing in this condition. Before maximum torque, as speed is increasing, your torque is also increasing. That's why this is unstable operating region. Whereas if you see here, as speed is increasing, your torque is decreasing. That's why from here to here, that is called the stable operating region. So this is your stable operating region. And during this time, this is in the first quadrant, right? First quadrant means, and with the positive speed means that is forward motoring mode. And forward motoring mode is extended into the other region. If you are increasing the speed beyond its synchronous speed, that will entering into the other region, that is nothing but forward regenerative braking mode. Forward regenerative braking mode will get if you are increasing the speed beyond its synchronous speed, beyond omega ms. If you are increasing, or if you are increasing the rotor speed beyond synchronous speed, then it will enter into the other quadrant, that is second quadrant. That corresponding mode is called the forward regenerative braking mode. Okay. And if you are extending the forward motoring characteristics into the other quadrant below the 0 speed, or here speed is 0, right? Below the 0 speed or more than slip 1, then that will enter into the fourth quadrant. So the corresponding characteristics are called the reverse plugging, because the corresponding speed in the corresponding quadrant is nothing but minus omega m. That's why this is plugging characteristics. But whether it is forward or reverse, that decides the corresponding speed. As this is minus omega m in this quadrant, reverse plugging characteristics. In a similar way, if your motor is operating with RYB phase sequence, we'll get the forward motoring. By reversing the phase sequence, we can get the reverse motoring operation. Simply exactly mirror image characteristics will get with respect to the y-axis, will get in the third and second quadrant. So that means reverse motoring operation will get by reversing the phase sequence of the induction motor. Instead of RYB phase sequence, if you are using the RBY phase sequence, will get the reverse motoring operation. So for this reverse motoring operation, again, so the starting torque at 0 speed, you have some starting torque. Again, it will reach to the maximum torque. Sm is equal to R2 by X2. So this is your maximum torque corresponding slip. And at here, again, this is unstable region, because speed is increasing in the negative direction, as well as torque is also increasing. That's why this is unstable region. Only stable operating region is from here to here, maximum slip to synchronous speed, since synchronous speed. So the corresponding region is called the reverse motoring operation, because here your speed is decreasing as your speed is increasing, your torque is decreasing. Okay, this is torque is decreasing, right? That's why this is called a stable motoring operation. So as speed is in negative direction, that is called the reverse motoring operation. If your reverse motoring operation is extended beyond synchronous speed, then that will enter into the reverse regenerative braking, because in the negative speed characteristics quadrant only we are getting. That's why this is reverse regenerative braking characteristics. Again, here also up to here, the stable operating region, reverse regenerative braking operation. And if we extend before starting torque, then that will enter into the other quadrant, that is second quadrant. That is called the forward plugging, because the characteristics are entering into the second quadrant. When it is entered into the second quadrant, the corresponding speed axis is positive. That's why that is forward, and it is in the plugging mode, forward plugging mode. So this is all about the speed torque characteristics of the all four quadrant speed torque characteristics of the induction motor. We have seen here forward motoring, forward regenerative braking and forward plugging, reverse motoring, reverse regenerative braking and reverse plugging. So all these together in all four quadrants speed torque characteristics of the induction motor. Okay, thank you all.